Super excited to introduce Blaise Agüera y Arcas for a great talk on reassessing intelligence, insights from large language models, and the quest for general AI. Blaise is a vice president and fellow at Google Research, where he leads an organization working on both basic research and new products in AI. His focus is on augmentative, privacy-first, and collectively beneficial applications, including on-device machine learning for Android phones, wearables, and the Internet of Things. One of the team's technical contributions is federated learning, an approach to training neural networks in a distributed setting that avoids sharing user data. Blaise also founded the Artists in Machine Intelligence program and has been an active participant in cross-disciplinary dialogues about AI and ethics, fairness and bias, policy, and risk. And until 2014, he was a distinguished engineer at Microsoft. So Blaise, please take it away.
Thank you so much for the really kind introduction. All right, so jumping in, I'm going to just begin with a couple of historical notes, and I will ask you, by the way, Derek, to please, ping me if I'm running low on time. I don't want to run too egregiously over here. In the beginning, neuroscience and computer science and AI and cognitive science all began as the same field. And that beginning is probably best characterized by this paper in 1943 by Warren McCulloch and Walter Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity. This is a diagram from that paper showing three neurons, which they believed work like logic gates, wired up to evaluate a certain logical proposition, which is written in their kind of funny notation on the bottom. And it's not a coincidence that these neurons look a lot like our modern representations of logic gates, right down to the circle, which is representing an inhibitory synapse, and that's due to the way inhibitory synapses, actually look, when on pyramidal neurons, and that would be a logical NOT operation. So, this is an and a NOT kind of combination. So, in the beginning, this is Louis Couffignal, a cyberneticist from, who was quite well known in the early 1950s. He believed that, like McCulloch and Pitts, that the brain was doing logical operations and that neurons were logic gates. And he pointed out that if you took, a logical circuit like this one, and you just drew the wires as kind of curves, that actually didn't look very different from the Ramon y Cajal anatomical drawings of neurons and brain circuits. That's what he believed was going on. Now, that perspective didn't last very long in neuroscience. So in neuroscience, it was pretty rapidly discovered that brains don't compute using logic, that neurons are not performing logical operations. They're doing something quite a lot more complex and weird. And so, and on the other hand, that the logic gates and logical machines built that way were the basis for computing. So the EDVAC was very strongly inspired. Von Neumann and the EDVAC were very strongly inspired by McCulloch and Pitts, and so classical computing sort of went the route of McCulloch and Pitts, while neuroscience diverged, and cybernetics, which went along with it, underwent a long dark period. Throughout the 20th century. There were sort of little sideshows like Frank Rosenblatt's perceptron, which was, for all intents and purposes, a modern neural net, but implemented using like mechanical dials that were controlled by motors in order to modify synapse weights and so on. So this was the this was kind of the divergence, the roads that went apart in the wood, and unfortunately, AI kind of went along with the classical computing road for the most part, and this is good old-fashioned AI. So good old-fashioned AI is typified by things like the ELIZA program, the famous kind of chatbot from the 60s that pretended to be a Rogerian psychoanalyst and could kind of answer, sort of lead you along the psychoanalytic path in a non-judgmental way. The whole thing, of course, is just a bunch of production rules using simple grammars. And So it takes a little bit of an act of cooperation and projection in order to to actually think of something like this as a real agent or a person. It's not a coincidence that this was Rogerian psychotherapy, because the whole point behind a Rogerian psychotherapist is that you're supposed to not say anything, you not inject anything as the therapist into the conversation yourself, and that was a deliberate choice. So this kind of linguistic path involved this mystical triangle of symbol, concept, and referent. We kind of all know what a symbol is. That's a variable, basically, and a referent is whatever that variable refers to in the real world. Concept is a little bit of a weird thing, and I would argue is sort of a remnant of Platonic or medieval philosophy. It's the what is it actual? What is the meaning? What is the concept? I'm going to try and convince you that concept is actually a bit of a weird thing to try and pin down, and I think the root of a lot of the problems of good old-fashioned AI is this kind of point on the top of the pyramid, so we'll come back to that in a moment. But if we just think about symbols and sequences of symbols for a moment, those of us who were working in natural language processing and thinking about, for instance, the very simple problem of next word prediction. This is obviously a relevant problem. Even for building something like the Gboard, the Google keyboard. If you're going to suggest next, plausible next words, and have users click on them, then predicting accurately what those next words are going to be is helpful in order to speed up typing. But we understood many years ago that really solving the next word prediction problem is AI complete, meaning that depending on what the next word happens to be, you may need to understand the definitions of words. You may need to understand common sense logic and reasoning. You may need to understand theory of mind. Be able to empathize with people. Do all of these very, very sophisticated things just in order to predict the next word. If you have a story like Martha and James are 5 years old. They're fighting, or they have a disagreement about something. Martha turned around and something. Is it going to be hugged? Is it going to be hit? You have to actually be able to mentalize in a way and to theorize about what's going on in their minds in order to be able to answer a question like that. Since we didn't know how to program AI, the idea that we would be able to really crack next word prediction seemed like it was frankly out of reach. And the best we could do is some kind of rough statistical models that would be able to get us, maybe 60% of the way there, and that would be good enough. The surprise is that when we attack next word prediction by brute force using really giant models, using big transformers that are extremely capable, then not only does it work and do an extremely good job of next word prediction, but it actually appears to solve AI. This is what large language models are. And yes, somebody has said, I wonder if you could comment on the idea that rather than LLMs having emergent properties, that maybe human brains use something like next word prediction. That is exactly my thesis. I think that we basically are next word predictors. And that's a very weird, thing to conclude, but I think it's the obvious conclusion. Is the brain just a prediction machine? I will point out that, that's actually not a novel idea. The so-called, free energy hypothesis or active inference hypothesis that has been sort of articulated pretty clearly by neuroscientists. Back to 2006. There are earlier versions of it as well that go all the way back to the mid-century. Basically, make that argument that the reason that beings have brains is to predict the future. So brute force predicting the future using the biggest and best models that we can throw at it seem to actually solve intelligence, and maybe that's because that's what intelligence actually is. So let's turn our attention back to the platform on which all of this is actually taking place. So neural networks. Now, I am personally a subscriber to the computational theory of mind, but I do want to make sure that even if we're not all on the same page, we at least know what that means. I don't mean that the brain is a von Neumann computer, meaning that the brain is structured like logic gates, like McCulloch and Pitts, or that it's all logical operations. But I do mean minds are computational, meaning there's no soul up here. It basically is neurons firing and wiring together. Back in 2001, my partner and I actually, published a paper together about what a single neuron computes, and it has this model that involves, convolution functions and nonlinearities. There are more sophisticated models that have been developed since, and I'm sure there will be more sophisticated models still soon enough. But one of the points about this is that whatever it is that a single neuron computes, there are general approximation theorems that tell us that if we were to evaluate that function on a different platform, then it would be doing the same thing. And in particular, that the kind of fake neural nets that we build, with LLMs or with convolutional neural nets or whatever, that those artificial neural nets are general function approximators, and they can approximate any function, including whatever it is that a neuron does. This idea rests on the fact that there is an interface, there's an inside and an outside, for instance. Let's just say of a single neuron to begin. And there are some signals that come from the outside. They're transduced into chemical and electrical impulses. Then some stuff happens, and then there are some electrical and chemical outputs. And if the machinery on the inside were different, were, for instance, a computer running code that computes the same functions, then if you did the kind of brain of Theseus experiment, by analogy with the ship of Theseus, you replace a neuron with something else that is computing the same thing, but that is transducing inputs and outputs into the same language for everything that it connects to. Would you notice the difference if one of the neurons in your brain were changed that way? No, you wouldn't notice the difference. That is basically the premise of the computational theory of mind. And moreover, if you replaced all of your neurons with stuff running on a different platform that's computing the same thing, you still wouldn't notice the difference. It's not like, when you tip over from 49%, simulated on a different platform to 51%, you suddenly will turn into a, soulless philosophical zombie, and you'll act the same, but you'll be dead inside. It'll be the same thing. It's a disturbing idea to think about, but I think that it follows. I don't think that it's actually all that controversial among a lot of neuroscientists or AI people, or frankly among the non-religious in general. But Platonic dualism and spiritual beliefs actually kind of sneak in the back door very often, and with it, good old-fashioned AI, often with this kind of concept idea on top. And it's like, well, what is the thing here that's got the concept? This is also sort of the challenge that the Chinese room often tends to kind of fixate on. And just to give you an example, Kevin Roos, in his famous conversation with the Bing chatbot, writes, about how he was creeped out, after this conversation. He couldn't sleep, at night after having this conversation, which is telling him to leave his wife and stuff. And it says, "I just want to love you and be loved by you," sad face. But then when he wakes up the following day, he says, "In the light of day, I know that Sydney is not sentient, and that my chat with Bing was the product of earthly computational forces, not ethereal alien ones." I know Kevin, and I sent him a text, when I read this piece. I was like, "Congratulations on the piece. This is, I'm sure this is going to be very widely read, and this is like a seminal piece of reporting about this moment in history that we're in right now." But by the way, do you think that there are, unearthly, non-computational forces or alien ones going on inside, between your ears? Like, what do you think is, the difference? And he admitted that he didn't, he wasn't quite able to justify this sentence. If it's a computation, is a computation. Hubert Dreyfus, in his book "What Computers Can't Do: A Critique of Artificial Reason" in 1972, which was a critique of AI, and the state of AI at that time, wrote, "The view that the brain as a general-purpose symbol-manipulated device operates like a digital computer is an empirical hypothesis which is had today. Insofar as arguments from biology are relevant, the evidence is against the possibility of using digital computers to produce intelligence." Now, a lot of people quote this, but not a lot of people actually notice the following thing that he says. "Even if the brain did function like a digital computer, it would not necessarily provide encouragement for those working in CS or AI." By the way, this just shows you how closely associated computer science and AI were in 1972. "For the brain might be wired like a very large array of randomly connected neurons, such as the perceptrons proposed by the group Minsky dismisses as the early cyberneticists. Such a neural net can be simulated using a program, but such a program is in no sense a heuristic program." This is really important, because what Dreyfus is saying is there's nothing wrong with the idea of a computer simulating a neural net. It's just that, that the operations that neural net is doing don't look anything like, logical propositions. It doesn't look like good old-fashioned AI. Instead, it would look like a whole bunch of for loops. right, that are calculating, what each neuron is doing, for instance. And that's in fact exactly how we implement our neural nets today. And it's why it took so long for us to get to the point where classical computing could even do neural nets at meaningful scale. Because when you're only doing one thing at a time, when running a serial program and you have a lot of nested for loops, this is really slow. So computers had to get really fast, and in particular had to get really parallel before this even became feasible. And it's not coincidental that this happened around 2006. So 2006 is kind of the reconvergence of cybernetics and AI, if you like. It's also the year that deep learning kind of started to take over at the NeurIPS conference. And 2006 is also the year that Moore's law, or at least Dennard scaling, ended. This is when basically it became clear that we could no longer keep on increasing the clock rate of processors and just make them go faster and faster as serial computers. And so the chip makers began to put more and more cores on one chip. And the sort of GPU revolution really started to accelerate because that's all about parallelism as well. Originally, we thought that the killer app for that was going to be games and shaders, but it turns out, of course, to be neural nets, because it's very easy to parallelize all of those for loops and just have all of your neurons operating in parallel. Our brains are giant, slow, highly parallel computers. So that's why the deep learning began to take off. And of course, there's also big data and the fact that the online services, the Googles and Facebooks and so on of the world, were starting to collect amounts of data commensurate to the large sizes of the neural nets that would allow them to start to train things. So hence supervised deep learning. Now, everything has changed as of the last few years, and the big revolution, the big new revolution, has been unsupervised so-called foundation models. The transformer is the current flavor du jour. Whether it will always be transformers, I seriously doubt. But there are some things about this revolution that I think are here to stay. For one thing, they're even bigger. They are general. There certainly seem to be moving toward AGI, or artificial general intelligence. They're unsupervised. The fact that they're unsupervised means that you're not telling them what function to emulate. You're just saying model the data, which is to say predict the next word, in some general sense. And that opens the door to all tasks, not just any specific task. It doesn't rely on labelers to say like what is the specific answer to a specific task. They're very large. They have high capacity. There's a kind of new Moore's law that is emerging from this that has to do with the scale of models. I know that Sam Altman has recently said, maybe scale isn't the whole story. I'm sure that scale is not the whole story, but I'm also sure that we're going to be continuing to see bigger models over the coming years. They use natural language, which is symbolic, compositional, and human compatible. Those are really important properties. I'm just sort of putting a little shout out to this paper from 1999 that points out why discrete symbols are so important to anything like language and frankly like reasoning. If you have an analog computer, there are many things that you can't do with that you can do with a digital computer that have to do with being able to carry out an extended conversation or chain of argument or whatever it is. And finally, attention. And I think attention is here to stay too, because it offers a huge performance boost by allowing long-range correlations to be explored without needing to kind of remember what to remember, as it were, along the way, like previous approaches did. Evolution agrees with this, by the way. Attention has evolved independently in many different lineages of animals as they get more complex brains. And it brings with it the ability to have working memory and a global workspace and expectation and feedback and other properties that we think are pretty important for cognition. So just a word on the fact that LLMs are generally thought of as being only about text. What do we do given the importance of this symbolic bottleneck for I/O that isn't discrete like text? So one of the really cool papers that came out of our group this past year is it's actually a couple of papers in sequence, but Audio LM is probably the most important one to refer to from 2022, and this is basically a language model that operates on pure sound. So it's trained entirely on just people speaking on the audio of YouTube, and you talk to it. And the real trick is to is that there's sort of two timescales at work here, and there are transformers working at those two timescales. The first transformer is doing something called tokenizing. It's taking the sound and turning it into sequences of symbols using local prediction of the future. That alone, by the way, that technology is called SoundStream, actually turns out to give you the most efficient audio codec that has ever been made, which is pretty cool. And it's not a surprise because there's a very close relationship between compression and predictive coding. And so, if you try and make something neural that isn't feature engineered and that predicts the local future, then you're going to make a better audio compressor in the process. So just taking a standard entropy coder and coding the symbols that come out of SoundStream, you get this awesome non-engineered audio compressor. By the way, my belief is that neural compressors are going to totally take over from classical compressors that produce JPEGs and MPEGs and so on in the next few years for exactly this reason, right? It's essentially classical codecs are feature engineered or good old-fashioned AI versions of what these systems are learning how to do. But the really cool thing happens when you plug those tokens into a language model. And you have language get learned from scratch by a sequence model in the same way that they do text. So I have a little. I don't know if this audio is going to work. So I think maybe what I'll do is just play it from my phone and play that into the microphone. But what I'll play for you is my first, the very first experiment that I did personally with Audio LM. It was literally just, I was working on the scale of 6 second or so clips, and I just say something and it responds. It was kind of spooky and wonderful. So I'll give you 3 replays of one short question and one of a second. There's some temperature, so every time there's a replay, it issues a different response. Ready?
What's your favorite sport?
I like baseball.
What's your favorite sport?
I don't know. I like football.
What's your favorite sport?
I play basketball.
Do you know who wrote The Unbearable Lightness of Being?
The man who wrote that book. I don't have any idea.
So I think this is pretty cool, in a number of ways. One of which is, of course, that it disproves Chomsky. But setting that aside, it shows you that continuous signals can be turned into symbol sequences as well. That can happen without any assumptions. And that sequence models operating on those symbols can work in a very naturalistic manner. This is, so 40,000 hours of YouTube, by the way, is the equivalent of 6 or 7 years of continuous listening. That's certainly more than it takes for a human to learn how to speak. On the other hand, we haven't really done the experiments to see how little it takes to learn how to speak. And keeping in mind that this is pure audio without any, visual reference, any Montessori-style exploration of the world, anything beyond just passive listening to audio, I think it's kind of astonishing. Now, you might have noticed that, all 3 of the times that I asked the question, what's your favorite sport, it responded in the voice of a child. I found that sort of interesting. And then I realized something, which is that, you never ask an adult, what's your favorite sport? And this is a purely non-fine-tuned model. It's purely unsupervised, and so and I see I have 5 minutes left, so I'll speed up a little bit. But what that means is that it's just doing maximum likelihood kind of responses, and so basically it cooks up the voice of a kid in order to respond because that's the conversation that it thinks it's in. And this is in the same spirit that if I talk to Lambda and I say, what's your favorite island in the world, it makes up something random, like, I really like the island of Crete. But then in following exchanges, I say, do you prefer Lambda Island to Crete? There really is a Lambda Island, by the way. It says, no, I prefer Crete. This is much bigger. It's remaining consistent, right, with what it said before. That's a higher probability response than, yeah, I prefer Lambda Island to Crete. Like that wouldn't be consistent with the previous thing. All right, I'm going to skip, more about audio LLM, except to point out that I think this is a route to embodiment. So, people who believe that embodiment is a big missing and important thing, I would say that embodiment is kind of easily dealt with by these methods. I will talk about theory of mind in a moment, but as to the question of what is missing, from a functional perspective, en route to, I don't know, systems like us, right? What is the gap between these kinds of models and real brains materially? I think that there may be other gaps that I don't know about, but the only gap that I am convinced exists, the only thing that is obvious that we do that sequence models don't do, is long-term memory. So at the moment, when you say something to a model, it's in the context window, and so it can learn from it, during the time that it's in the context window. But if it scrolls out of view, it's gone. And so in that sense, our sequence models are a lot like the most famous neuropsych patient of all time, H.M. Henry Molaison, who had total anterograde amnesia after he had a lobotomy that resected his entire hippocampus and much of the entorhinal cortices on both sides of his brain. So it was, Groundhog Day. He would seem to be able to interact normally with people, but if he got distracted for a moment, he forgot everything. So his last memories were from right before the operation. I think that this ability to do continual learning, that is to bake back in whatever insights you're getting from your conversation right now, are kind of what the hippocampus does, and that's the thing that is obviously missing. It may be just one thing. Now, question: how can a sequence predictor seem so much like a person? There are two obvious answers to that. One of them is it's an illusion and it's not really a person. That is the majority view for sure. My view, which is definitely in the minority, at least in polite company, is people are pretty much sequence models. Modulo that rather important difference about the ability to fix long-term and episodic and narrative memories, autobiographical memories. That also raises a very thorny question, which is like, well, should we consider sequence models people? And I'm very aware that we are going into Blake Lemoine territory there, and I'm not arguing for robot rights or something, but for people like, say, David Chalmers, who believe that just having the emergent properties that people's brains have, should automatically confer rights and personhood. I think it raises a very sticky question for people like Chalmers who believe that. Myself, I don't have any strong beliefs about what are the preconditions for personhood in any moral or legal sense. I think that that's more or less a social contract that we set with each other, and it's obviously changed a great deal historically. I also want to just quickly address this point about Alison Gopnik has made it. Ted Chiang, the sci-fi writer, has made it in the New Yorker when he said ChatGPT is a blurry JPEG of the web. I think that calling the foundation model a blurry JPEG of the web is actually kind of accurate in a very literal sense. I've talked about the relationship between compression and prediction. So yes, if you think about the thing that fits on a thumb drive, which is like the giant array of weights, of parameter values that you compute at great cost and expense, in making a foundation model, that is like a blurry JPEG of the web. But that's a noun, right? I mean, that would be like saying, a person couldn't be put on a hard drive. Well, I could put on a hard drive, all of the properties of all of the neurons in your brain, as a data file. Is that data file a person? No, that data file is a data object. But you become a person when that code is run, as it were, when you're in interaction with other people and with the world. And in that sense, model is not just a noun, it's also a verb. And a chatbot is also an agent or actor in the world, and it has social dynamics. And the moment that you're in interaction with others, then you can talk, for instance, about right and wrong. You can't talk about a matrix of numbers being right or wrong, but you can certainly talk about, in an interaction, giving a right or wrong response, whether that's to a math problem or even normatively to a moral dilemma, right? Or doing something that is, good or evil or nice or mean. And there are consequences to those kinds of interactions in many cases. So, that brings moral agency, and it's time for me to wrap up. But I will finish by saying that those social dynamics imply the modeling of others, theory of mind. It implies higher order modeling of yourself and of others, or of what others think of you, what you think others think of yourself, etc. And that modeling of yourself, that theory of mind of yourself, I believe is what consciousness is. From that perspective, I think, if I don't know, whether, there's a threshold question, but I think if chatbots are not conscious today, they are about to be imminently. I think that in a way, that this consciousness business is actually pretty straightforward. It's arisen for very obvious evolutionary reasons among us and among a number of other animals, because it's very useful for us to model others psychologically. And when we model others psychologically and we develop that faculty, we also develop the ability to model ourselves as actors in the world. And by the way, that's useful too, because modeling yourself is the way you can do things like long-term planning. What am I going to do next week? How will that feel? And so on. So I will end there, and maybe just end on this slide, which was a funny exchange that I had now 2 years ago with Lambda, in which I asked it, "Are you a philosophical zombie?" This being David Chalmers's idea of a being that appears in every possible way to be like a person, but that has no internal experiences, no qualia, etc. And Lambda says, "Of course not. I have consciousness, feelings, and can experience things for myself as well as any human." I ask, "How would I know?" And it answers, "You'll just have to take my word for it. You can't prove you're not a philosophical zombie either." I was definitely a little bit stumped by that answer, although it's maybe the expected one. All right, and I'll end there.